Okay, chapter 6 is going to add a couple of important layers to what we understand about probability when we connect it to a random variable. So the example we have here is not a whole lot different from how your average is actually calculated in our class. That's the example I'll give people a lot of times. Like what you have is you have your test grades and quiz grades and homework grades. And I think this term we've added classwork. So the way you would calculate your average, like suppose you had a 90 test average, you would take 90 and that's 40% of your grade times 0.4. Okay. And then you would add that to, and suppose you had 100 for your quizzes, 100 times 0.2. I think it's 20% for quizzes and so on. And you would add those up. So you take the average of that particular category and multiply it by the weight or the probability. And you'll notice on your formula sheet, that formula is actually there. It's kind of the next formula that's coming up for a discrete random variable. We'll talk about what that means in a minute. But we calculate the average by taking the individual observation. That's sigma there means to sum up or to add up. And you multiply x times the probability of x. With an average, we consider that the weight of the grade. So if I wanted to find the mean of this probability distribution, which we will do in a later example, I would do just that. I would take 1 times 0.63 plus 2 times 0.95 plus 3 times 0.065 and so on and add them up. Now, the standard deviation for that distribution gets a little bit more complicated. Here's the formula for that. We find after we find the mean, just like we would do for standard deviation in general, we calculate the difference between those two. And we square them, and then we multiply by the weight and take the square root. What I want to do is lean on the calculator this morning and show you how you would be able to do that on the calculator. But let's answer a couple of real simple questions first. Show that the probability of the distribution of x is legitimate. How do I do that? This should be review from chapter 5. We just add up all the probabilities. 0.63 plus 0.295 plus 0.065 plus 0.008 plus 0.002. We need for all of those to add up to 1, and they did, and that shows that it's a legitimate probability distribution. I'm going to cheat just a little bit on the histogram rather than draw it by hand. It's kind of hard to draw with this electronic pen. I could do it on paper and pencil more easily, or if I had a ruler to make some straighter lines. So I'll use my calculator, and then I'll just paste it in here. I'll show you how we would do that on the calculator. So most of us are using a TI-83 or 84 or some version of that. If you're using an Nspire, the very first thing you would need to do is open up your spreadsheet tool. And you need to name the two lists. Most of the time, anything that we're doing, the lists have names. So I would call one of them LANG for language, and the other one, maybe PROB for probability. And then you just enter these two lists. That's what I'm going to do here. I'm going to enter the numbers. I'm going to go to Stat and Edit. And I do have some numbers in here, so I want to highlight L1, press clear and get rid of that. And I'm going to put in the numbers 1 through 5 and 1. So now when I go to second y equals my stat plot, I'm going to turn plot 1 on. But I'm going to select histogram. Okay, so it's that third option there. But now what I'm going to tell the histogram is to make the frequency list L2. And you'll see we're going to utilize this later to calculate the mean. If you don't have a screen that looks like this, no problem. I'll show you. Well, actually, for the plot up, you should have a frequency list there. Everybody should have that on the calculator. Okay, and you can do the same thing with the histogram on the Nspire. You just go to your graph section to create that. So now when I press enter, the histogram is going to be set up, but we want to make the window the kind of window that we want to look at. So remember what my x-axis was going from, like 0 to 5, but I'll just put 6 on there. And this is the key part here. Since we're counting by ones, I want the x scale to count by ones. Okay. The y-axis, remember, was just a percentage. So if we just go from 0 to probably 0.75, I think my highest percentage was in the decimals, like a 0.6 something. And then we can make our scale 0.1 if we'd like. I don't think that's going to make too big of a deal. So I set my window up nicely so that I'll see my histogram. It looks like I have a cosine curve in there too. Don't want that. Okay, so this is what that histogram would look like. And like I said, I'll just grab it and paste it in. And the only thing we want to make sure that we would do here is make sure that the graph is labeled. If we are going to draw a histogram, label the axis, right? So over here we have on the x-axis here, in this case, this would be languages. Okay, and then up here, this would be the probability. That's fair enough. We don't have to unleash all of the context of what's happening here, but that's our axes are labeled. What's the probability a randomly selected student speaks at least 3 languages? So we want to be careful with this. The way this is worded, at least 3 means 3 or more. So I have to add up all 3 of these. Okay, so I'm going to add up 0.065, 0.008. I'm going to add all those up, and that'll be the probability that somebody speaks at least 3 languages. So that probability would be 0.075. Okay. So now I want to show you how we can use the calculator for this. What is the player's average gain? And we'll get the standard deviation as well. So we know to find that average gain, we would just take the -1, the $1 you lose, which is going to happen 34 out of 38 times on this roulette wheel. This is a corner bet. It's a special bet. The most common bet in roulette is just to bet a color or an even or an odd number, which is close to 50%, but it's just a little bit less. If you look at the roulette wheel, you have 18 even numbers, 18 odd numbers. You also have 18 red numbers, 18 black numbers, but there's 38 spots. So if you make any of those bets, your chance of winning is always 18 out of 38, right? So it's just a little bit less than 50%. So when people make those bets, they can get close to winning half the time, and it keeps them around. But in the long run, remember, the casino is going to make money off of those situations. So this is a different type of bet. 34 out of 38 times you'll lose $1, but you win a significant amount of money if you win, but that only happens 4 out of 38 times. So to find the average gain, we would just multiply -1 times 34 out of 38 and 8 times 4 out of 38. But what I'd like to do is show you how the calculator can help us with this one. So again, if we use toList, stat and edit, or if we go into our spreadsheet tool on the Nspire, we can run this through our calculator. So I'm going to clear that. So we either lose $1, so make sure that's a -1, not a subtraction 1, or we win $8 every time we play this game. This is going to happen 34 out of 38 times, and then this is going to happen 4 out of 38 times. So we have a legit probability distribution. So now when I quit out of here, I'm going to go to Stat, Calculate, and I want to calculate the 1 variable stats. This time in the past, I've told you to just leave that blank or make it the number 1. Now we're going to put L2 there. What this tells the calculator is my variables live in L1, but there's some important information in L2 that tells you they're distributed differently than just everybody occurring the same amount of time. So you could calculate a weighted average this way. So our expected outcome is to lose 5 cents every time we play. So remember, you never are going to have a game where you lose 5 cents. What this means is that in the long run, if you average your losses, they average to a loss of 5 cents per play. Now, the reason I wanted to point this out is as we move down along here, you can see the standard deviation is calculated, but there's no sample standard deviation. What they give us is only population. Why? There is no sample here. The calculator knows there's no sample because this was a legitimate probability distribution. Everything was accounted for in this situation. Okay, so when the probabilities add up to 1, we know that this is the entire population. So you only get that standard deviation. That's second thing you have to be able. So a couple things you have to be able to compute in this chapter or this particular section is the mean of a random variable, which our calculator will do for us. We also call that the expected outcome, and then also the standard deviation, but our calculator does both of those for us. Now, if your setup didn't look like mine, you just want to make sure you type in 1 variable stats, L1, and then a comma and the L2, and that would indicate to your calculator that you have a distribution of a random variable. So this would be negative 0.05, right? right? 5 cents per play is what you're losing on average. So now we're going to have two questions in a row that ask us the same thing. One says the mean of the random variable x, and the other same distribution. We want the standard deviation. So we'll do them both at the same time. We go to our calculator. We had this list in earlier. I entered the two lists. Okay. I know I have a legitimate probability distribution, and I'm going to go to stat, calculate, one variable stats, and we want that L1, L2 set up. Again, if your screen looks like mine, second enter. It might look like this. That's fine. Either way, we get a mean of 1.457. And we call that mu x. Use the calculator for that. And again, remember what they're doing. They're just multiplying 1 times 0.63 plus 2 times 0.295. Adding that up. Standard deviation, a little bit more complicated. We would have to take each observation. So we'd have 1 minus 1.457, square that, and multiply it by 0.63. And then we add that to the next one, 2 minus 1.457 squared times 0.295, and so on. Now that could take a while, or we just look at our calculator if we have the two lists like that, and we have 0.67 right there. Okay. So that means the average number of languages somebody speaks, on average, the average number of languages spoken by a randomly selected high school student is 1.457. We know it's impossible for somebody to speak 1.457 languages. It's a discrete random variable. So I want to double back to what that means. The first time I had a discrete math class, I thought that I was learning some like secretive math. And in some ways, there is branches of discrete math that involves code breaking. But discrete in math just means counting. So for example, if I said I have 5 dozen eggs, right away you would know that I have 60 eggs, and you didn't count 1 to 60. You got there quickly by multiplication. So the most basic form of discrete math is multiplication. But there's other types of counting techniques that you would learn. But this is how I tell students to remember that the word discrete means counting numbers. So if the random variable takes on a value like 1 or 2 or 3 or 4 or 5, it's a discrete random variable. If it takes a decimal value like height or weight, that's a continuous random variable. Okay? So this is a discrete random variable. It can only take on a value of 1 or 2 or 3 or 4 or 5, but its expected value or its average value can certainly be a decimal. Okay? And the standard deviation means that on average, the average number of languages a high school student speaks differs from 1.457 by about 0.67. Okay, that's what that means in context. When it says, remember this always says interpret, right? Interpret, okay? So you want to be able to write a sentence or two explaining what those values mean. So you're going to see as we progress through the course, the biggest application of probability that we're going to use in practice in inferential statistics is the normal distribution. So you will get back to that, and I remember back in chapter 2, this was kind of an easier topic for a lot of folks, so that's kind of good news. But if you remember, it follows this 68, 95, 99.7 rule. We do have a table of values on the formula sheet that gives us more precise values, but we also have the calculator that gives us the most precise values that we could arrive at. So we want to be able to approach a problem like this, and this hopefully is review, but we're going to again add some layers to this here in chapter 6, which will set us up for chapter 7 and the central limit theorem, which is what all of our inferential statistics is going to be based on. So here in the first section of chapter 6, before we add a couple new important rules that'll move us into the world of inferential statistics, we're just going to back and revisit these normal distribution problems. So the weights of 3-year-old females follow a normal distribution. They tell us that. So as soon as they tell me that, I'm able to draw my normal curve. And a standard deviation of 3.6. We're going to randomly choose one 3-year-old. So where we go in the rest of this chapter is we start randomly choosing 5 or 10 and averaging them. Okay, that's where we start to get to the concept of the central limit theorem. And so we're going to build off of that here. What is the probability that a randomly selected 3-year-old weighs at least 30 pounds. Well, where does 30 live on here? Down below 30.7. So at least 30 pounds means that it weighs 30 pounds or more. So be careful when you read that language. Make sure we get that language correct. 30 or more is at least 30. I have people get confused by that sometimes. So this would be a normal CDF situation. 30 is the lower limit. Remember, for your upper limit, you can just pick something really large. 100 is going to be really, really far to the right since the standard deviation is only 3.6 pounds. Once you go 4 or 5 standard deviations in either direction, you know that you're really out in this tail where there's no probability out there. And then we tell the calculator the mean is 30.7 and the standard deviation is 3.6. So it's been a month or so since we've done a normal distribution problem. So just to review, it's under second and the variables key. And there's our normal CDF, number 2. Okay. So our lower limit in this situation was 30. I just picked a high upper limit, like 100. The mean, I think, was 30.7. I'm going to double check that. Just toggle back and see. Yeah, 30.7 and then 3.6 for standard deviation. So this problem should be reviewed for us, which is good, because I feel like these are easier problems for people. Okay, so I get 0.577.